So my name is Colin McCarthy. I'm a senior principal engineer, and I work on AWS EC2 on the network and VPC. I've been here at AWS 10 years, and before that I spent about 10 years as a network engineer as well. So my background is all networks. And today everything we're covering is networking related. We're going to cover some very quick VPC fundamentals, just a small review of what VPC is so that the rest of this makes sense. Then we're going to cover AWS PrivateLink for AWS Services, a little bit about how PrivateLink works under the hood, both because it's interesting and because it will help us make sense of the tenancy models for PrivateLink and some of its capacity and scaling limits and so on. And then we're going to talk about PrivateLink for customer and partner services, and how you can use PrivateLink to either offer services directly into VPCs or to expand how many VPCs you use to support microservices and so on. But as I said, we're going to start with just some very quick review of what VPC is. And so VPC stands for Virtual Private Cloud, which is an offering we have for EC2, our Elastic Compute Cloud. And a VPC is essentially a virtual data center that you can create using our APIs or consoles, and then you can launch and manage cloud resources inside that VPC. So when you create a VPC, because it's private, you get to assign the IP range. So here we have 192.168/16, so that's your own private network. You get to choose what the range is. Actually, you can use a public range as well if you prefer. And all of the resources that are inside the VPC use IPs from that range, and they can talk to each other. And those resources can be things like instances, or containers, or databases, load balancers, and all sorts of other things. You can connect that VPC to your own network by a few means. So you can connect using our Direct Connect offering to your own premises, whether that's a data center or an office. And we also have a VPN offering. So if you want to connect in using a VPN firewall or similar device like that, you can also bridge networking between your locations. And everything should be able to talk to everything else using those private IP addresses. And that's all we really need to understand about VPC for the rest of this presentation to make sense. So a few years ago, we launched VPC Endpoints, which is an additional offering that you can launch or connect to your VPC. It launched in 2015 and has supported Amazon S3 and DynamoDB. And the idea with this is, previously before VPC Endpoints existed, the only way to connect to, say, Amazon S3 was to have an internet gateway and for your traffic to kind of logically leave the VPC and connect to Amazon S3. And many customers preferred that the connectivity would stay private and there'd be more control over how resources are accessed and so on. And so we launched support for VPC endpoints. And the way that works is the services keep their public IP addresses. So Amazon S3 still, in DNS resolves to public IPs, same for DynamoDB. But the connectivity is plumbed directly into your VPC. It's not going out over the internet or anything like that. And there is support for enhanced security policies. So for example, on S3, there are bucket policies, and you can lock down an S3 bucket and say it can only be accessed from certain VPCs. And you can say a VPC can only access certain buckets, and so on. This form of endpoints are now called gateway endpoints. We call these gateway endpoints because they kind of look and feel like a traditional networking gateway, in that there's a public IP range and a route in a routing table, and and that's how connectivity is provided. And now, as of last year, we have PrivateLink for AWS Services, which is the new form of endpoints that we're supporting going forward. And our goal is that all AWS services will be accessible as PrivateLink endpoint services eventually. So the main kind of conceptual difference with PrivateLink is that whereas gateway endpoints are kind of a connection between things, so you've got this secure private connection between your VPC and S3. With PrivateLink, it's more like the service is in your VPC. And so what does that mean? It means that the service itself uses a private IP address from your own VPC's range that you've decided. It actually uses one or more IP addresses, one per availability zone. And what that means is that the service can then be accessed from your own premises. So today we support AWS PrivateLink access over Direct Connect, and we'll be adding VPN, and it simply works. You can connect to the service over that private IP address, and there's no need for complicated routing configurations or policy-based routing or connection rewriting or any kind of complicated hacks. It simply works, and so that means you can have pretty seamless experience. So, for example, if you're developing software that uses endpoints, you can be testing and developing that software on your desktop or laptop at your office and connecting to the private IP address and checking that everything works. And then when you deploy that code to the cloud, everything stays the same. And there's no need for extra workarounds or having it operate in two different modes, which would obviously be inconvenient. We launched PrivateLink for AWS Services on November 8th last year. It's already been pretty popular. We're seeing a lot of people provision PrivateLink endpoints. We've supported Kinesis and the Kinesis Streams APIs, the EC2 APIs, so for launching and managing EC2 instances, the ELB API for launching and managing load balancers, EC2 Systems Manager, which is a web service that lets you manage fleets of EC2 instances and containers, the service catalog for discovering services, and as of the last few weeks, we now also support the KMS, the Key Management Service. And so as you can see, a lot of these services are very much targeted at kind of command and control or ways in which you would just need to manage fleets of things, and that's based on feedback from customers. We've prioritized those because there are cases where customers want to be able to operate VPCs that have little to no public IP connectivity, but still do useful things like launch instances and manage their fleets and run tasks and get and so on. In fact, if you use S3 or DynamoDB or EBS or EFS as your storage system, you can actually run a fleet of VPCs or run a fleet inside a VPC that has no public connectivity at all. Still have it do useful work, still issue it tasks to do via, say, the Systems Manager service, but have that data then exported via Kinesis or S3 or DynamoDB or EBS or EFS, and make useful work of a completely compartmentalized, no public IP connectivity at all VPC, which is a pretty cool use case. All of the IP connectivity is fully private. So because everything's using private IP addresses, that means there's that additional layer of kind of defense in depth that would prevent anything from being accidentally disclosed publicly, right? So the endpoints are only exposed over private IP addresses, no matter how you configure your routing setup or how many routes you export or re-advertise and so on. It's pretty hard to ever have those advertised on the internet or inadvertently exposed. which means these endpoints are more defended from just attacks such as password exhaustion attacks or DDoS attacks and so on, because they're simply not reachable. So that's an additional layer of defense over services that have public IPs. And then the last item here is that when you create an endpoint and use one inside your VPC, it obviously uses a private IP address. Well, we override DNS within your VPC, so that, for example, if you try to go to the Kinesis API endpoint, we will make that resolve to the private IP address from within your VPC, so that you don't need to do complex DNS hacks or any kind of overriding yourself, as long as the traffic is coming from inside that VPC. You can turn that off if you prefer. That's optional, and you can use your own DNS setup to do that instead. The PrivateLink endpoints, when you provision them, they also have regional and zonal names in addition to the name we override. And you can use those explicitly, so you can connect to the regional name. I'll show you an example of one of those in a bit. Or zonal names if you'd like to keep your traffic within certain availability zones, both to save money on any kind of cross-zone data transfer, or because you've got extremely low latency requirements and you want all that traffic to stay inside the same zone where the latencies are obviously lowest, or because you've got strong isolation semantics and you want to be able to operate every zone independently. You've got the freedom to do those if you want to use the zonal names. PrivateLink endpoints also work with VPC security groups, so you can create and manage kind of firewall-like policies that apply to these endpoints in a very native way. PrivateLink endpoints kind of look and feel like any other interface in a VPC, such as an instance or a container, and the same security groups work. You can also use IAM policies with VPC endpoints, and you can construct policies that refer to traffic hitting certain endpoints and so on. And as I mentioned already, they work with Direct Connect. So this is an example of I've created a Kinesis Streams endpoint in a test VPC, and so if you look right at the very bottom, you can see that there's the kinesis.useast1.amazon AWS name that you'd be very familiar with. And as I said, we've overridden DNS, so that just works from within the VPC. But you can also use these other kind of long and more cumbersome names to access the endpoint. So you can you get a name that's just purely regional, and you get ones that are zonal, right? So the one at the top there is the regional name that's specific to my endpoint in my VPC, and that's kind of all embedded in the name there. You can see VPCE-04 blah 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 blah. That's just my endpoint, and then you can see the local zonal ones, USD1C, B, A, and so they're all there free to use if you'd prefer to be able to restrict how things are being routed. And that's from the kind of client or consumer side. If you want to use an AWS service via PrivateLink, it's fairly simple. Go to the Endpoints tab in the VPC console, and there's a directory there that lists all of the ones you can launch, and you tell it which availability zones you'd like to launch it in, and you launch it, and it works. There's the experience from the customer or client kind of side is very straightforward. And so before we get into the more complicated case of how PrivateLink works if you want to vend services like this, it's worth getting a little into Hyperplane, which is the technology that underlies PrivateLink and makes it all work. And so Hyperplane is a system that we've had in production since 2015, which is based on the S3 load balancer, which preceded it by quite a few years. And Hyperplane supports the Elastic File System web service, VPC NAT gateway, our network load balancer, and PrivateLink. And what it is this kind of massively scalable and fault-tolerant distributed system that manages network connections. And it's just part of the core VPC technology, and it's handling all of this PrivateLink traffic as well as the traffic for all of those other services. And it kind of sits in the fabric of VPC at the networking layer, where we have our virtual software-defined networking. And as I said, it's a distributed system. It's made up of what we call Hyperplane nodes. And these are all nodes that are handling traffic and managing the connections. And they're fault tolerant and redundant and scaling and so on. But they're also making transactional decisions. So what happens is when you create an endpoint, what's happening is a virtual hyperplane resource is being created for that. That's mapped to several hyperplane nodes. And those hyperplane nodes kind of intercept connections at the network level and decide what to do with them, right? And they make transactional decisions like this backend target should get that connection, and they share that state in tens of microseconds so that even if any hyperplane node were to die, or even many hyperplane nodes were to die, a connection wouldn't die. So the system is highly fault tolerant and highly scalable. In fact, it's so fault tolerant because EFS is one of its main use cases where connections can last months to years. So it needs to be very, very resilient. For NLB, what's going on is that Hyperplane just selects the target instance or IP or container that should handle the connection, right? So if you're using a network load balancer, that's also a Hyperplane resource. And when it gets connections, it just decides which backend they should go to. So like many parts of our network, Hyperplane is a multi-tenant system. It's shared, which means it can be extremely scalable and cost-effective. And because that hooks into how our capacity is managed, it's worth understanding just a little bit about how that capacity is shared and how things are kind of divvied out. So we use a technique called shuffle sharding. So if you imagine that we had a series of hyperplane nodes, here I'm going with a really simple example of just 8 that's not representative. I'll cover a more representative number later, but just to make the slides easier to follow, we're going to go with 8. And so imagine we've got 8 hyperplane nodes. There's a lot of kind of algorithms or ways we could divide up a set of resources between customers. The most naive is, okay, well, we have this system or service. Let's just share it between all of our customers. So, every single customer might get any one of these 8 nodes at any time. And a lot of web services are architected like that. A lot of services are architected like that. It's not uncommon at all, but it does suffer from what's called the noisy neighbor problem, or if one customer were to have a very big spike, that might impact all 8 nodes, and everybody has a bad day, which is not what we want. Another strategy for that is what's called sharding, where, for example, here we might divide our 8 nodes into 4 shards of size 2, just so that there's still some redundancy inside each shard. And we might say, a quarter of our customers get the shard A, and a quarter of our customers get shard B, and so on. And in that world, if a single customer were to have a really large spike, then a quarter of the customers might be impacted, which is better than the first model, but still not ideal, right? That's still not something we would want to be desirable. So we instead use a technique called shuffle sharding. And the way that works is, so here we have 8 nodes. Imagine we gave a particular customer a set of 3, right? And we just pick 3 nodes at random, and we say, that's your 3. That's what you get. And then we have another customer come along. And for them, we give them a set of 3. And again, we pick them at random. So here we have an orange customer, and they've got their 3 nodes. And we've got a red customer and they've got their 3 nodes. And we see that there's some overlap. There's one node that they both were assigned. That one down at the bottom. But the overlap is partial, right? It's not complete. And if we do some really simple statistical modeling of this, we can actually measure what the overlap would be like. So just sticking with these numbers, if we had 8 nodes and we chose 3 each time for each customer, then approximately, if I picked any one customer and then said and measured, well, what percentage overlap do you have with other customers? Well, about 18% of the time, there's no overlap. About 54% of the time, there's 1 node overlap. About 26% of the time, there's 2 nodes overlap, and so on. You can see that, and then we get down to 2% overlap for all 3. If we use a more representative number, right? So in Hyperplane, we actually design for about 100 nodes and assign each customer a set of 5 just to begin with. If we look at the math for that, then everything improves quite a bit. We see that actually 77% of the time there's no overlap between any 2 kind of customers at random. And then 21% of the time there's just 1 node overlapping. Less than 2% of the time there's 2 nodes, and so on. And in fact, the other numbers are so low that we can exclude them. We can simply never assign customers in that way because we know where they're all been assigned. We can just exclude any cases where they overlap by 3 or more. And so the way we can operate our system is we can actually make a guarantee and say no 2 customers will ever share more than 2 nodes. And there's actually smaller than a 2% probability that they will even share 2 nodes. So in that world, what that means is that, if a single customer were to have a spike and generate an awful lot of traffic, instead of impacting other customers, what would happen is it would impact at most 2 nodes from, maybe 2% of the other customers. And that is very easy to handle. The system has more than enough overhead to absorb that. And those 2 nodes can simply be taken out of service for all those other customers very, very, very quickly and without impact. And then the original customer who had the spike gets the full capacity of their 5 nodes. So they get some relief too. And actually, we do some work to then isolate and provision them as we need to. And that's what's kind of going on under the hood to make sure that all this traffic can stay separate and all of these resources can be managed. And when you're provisioning an endpoint, what's really happening is under the hood we're reserving a certain amount of chunks of Hyperplane node capacity and provisioning them in these ways to make sure that everything can stay separate. We try to provision every Hyperplane resource, including PrivateLink endpoints, with about 5 gigabits of capacity by default. And then we scale them also in increments of 5 gigabits. So these numbers are very, very high. It would take quite a big spike in traffic or some kind of unexpected event to ever even trigger these mechanisms. But they're all there. And so now that we kind of understand Hyperplane as this system that's operating in the VPC network, provisioned in this way, and then it's multi-tenant and shared by customers, it's easier to make sense of PrivateLink for customer and partner services. And the way to think about it, kind of logically, is that it's a combination of NLB and PrivateLink. And that, we can offer services between multiple VPCs where we've got the backends or targets in the provider VPC, that's the one on the right-hand side, accessed on the client VPC on the left-hand side. And as we've seen, since Hyperplane supports both PrivateLink and NLB, in reality, they're the same thing. So we expose them as 2 different logical constructs, because that makes it far easier to grapple with in the console and APIs and so on. But really, in the underlying network, it's just one system that's making all of those work. And so the way that this is useful for 2 kind of main use cases. One is for service providers. If you want to offer services securely between or directly into customers' VPCs, just as we do. You can now do this with AWS PrivateLink. And you can also optionally integrate with the AWS Marketplace to sell them via our SaaS Marketplace. And then the other use case is for microservice architectures. So if you want to give each microservice its own VPC, for example, you can do that. Or maybe you have a central VPC that has a large number of microservices that you then vend into kind of orbital client VPCs. We see those patterns a lot, especially from some of our bigger customers who need to be able to manage things between teams. On the client or customer VPC side, not much changes. If you go to the endpoint tab in the VPC console, it's really just, okay, well, if instead of launching an AWS service, you can choose to either find a service by name, so you type the name right in there, you get it from your provider, and everything else you pretty much proceed as normal. Or you can look it up in the AWS Marketplace directory. But it's all, again, quite simple on the client or consumer side. There's really not much to it. On the service or provider side, there is more to it. So there, what you do is you start out with a normal network load balancer. So that's an ELB offering that lets you manage a very highly scalable, fixed IP address, network level load balancer that can spread connections across instances, IP addresses, even if they're behind Direct Connect, or containers. And you just create and manage that NLB as normal. You can use auto-scaling groups, you can use health checks, you can do all the regular things, you've got all your usual metrics, everything. You're charged for it as normal. But you can now associate that with an endpoint service. So when you create an endpoint service in the endpoint service tab in the console, you choose the availability zones you want to support, and you can decide if endpoints need acceptance or not, which just means when customers try to use them, that they have to be accepted by you or not. We have a workflow engine for all of this, driven via notification events with SNS, so you can create a topic. And so when customers try to launch and manage endpoints for your service, you can get SNS notifications, and you can use something like Lambda or step functions to handle those events. And so if you need to create and manage resources associated with your service on your side, you can have those triggered by these lifecycle events. One common pattern that we see, and it's very useful, is what we call the wildcard pattern, which is if you want your service to work with SSL or TLS, it's really convenient to create a certificate, a wildcard certificate for, say, your super cool service. And then when customers create endpoints, intercept the SNS notifications for them, and then create CNAMEs for them. So like per customer CNAME. So here I have one for me, right? column.supercoolservice.com, and that would be a CNAME to the endpoint that was created for me. And then you could give the customer the CNAME to use, and it just works. Very simple. This is the pattern we use for our own services. So for example, S3 buckets, CloudFront distributions, RDS databases, and so on. All have those, simple resource names dot service name. And it's a very convenient pattern that people are used to. So that's something we'd recommend. As I've said, this is all, our networking is zonal. So when you create the NLB, by choosing to put it in as many zones as possible, that will help you get the best latencies with other customers. Because, if you're in the same zones that they are, then you'll just naturally get lower latencies, and you won't incur as much cross-zone traffic. Do remember, though, that the zone names vary between accounts. Like your US East 1A may not be your customer's US East 1A. The names will always make sense in each other's console. So where you see US East 1A, they might see US East 1C, even though it's the same physical data centers and so on. All of this works today in region, does not work between regions. And that's mainly for availability and data sovereignty reasons at the moment. But we are planning to ultimately support this with our cross-region peering feature. If on the provider side, we have a few tenancy models, as I mentioned before. You may choose to create a private PrivateLink NLB for every single client or customer, make things very single tenant. So for example, if you want to have dedicated backends for each customer, that would be the way to go. If you want to do a multi-tenant mode where you use the same backends on your side across many customers, you can just simply use the same PrivateLink NLB. But then how do you tell which traffic is from which customer? We have a few mechanisms for that. The first mechanism is just to use accounts, use traditional passwords, security tokens, and so on. Just kind of ignore the networking layer. Maybe do things as you were previously. You had an internet-facing service. The other is to use separate NLBs anyway that are going to different listener ports on your targets. And so you can then use the ports to tell which customer traffic is for. And that's convenient if you don't want to have to change how your application works at all. And then the third method is that we actually have this proxy protocol v2 preamble, which we can put kind of as a header on connections that kind of looks like this. It's a binary format that specifies here's the VPC this traffic is coming from. That works quite well, but does mean that you have to patch your software to understand this preamble. Typically, that's quite easy. We've seen customers do it in about a day or so of development time, but it is something you have to have the capability to do. So if you don't have the ability to patch your application, maybe one of the other mechanisms might be better. In terms of costs, the provider side pays for NLB costs as normal. The client side pays for PrivateLink endpoint costs as normal. In both cases, we have an hourly charge that comes to about $18 a month for either having an NLB or for having an endpoint. And then there's a surcharge on data transfer that varies a bit by region. And you can also integrate with the AWS SaaS marketplace if you would also like to avail of its discovery and billing. So you can have your service listed in the AWS marketplace and they will do the billing for you and so on. And that all integrates with the standard SaaS marketplace billing model. So the main takeaways from all this are that PrivateLink endpoints are in your VPC, not something you're kind of connecting to, and that they work over Direct Connect. They're all powered by Hyperplane. And what's happening when you create these endpoints is that capacity is being reserved for you under the hood. That's really where that $18 a month goes towards. Reserving the 5 gigabit minimums and so on. And then you can now create and manage your own PrivateLink services, hopefully pretty conveniently using workflows and so on if you'd like. And then we also have more services coming all the time, both from ourselves and partners. So in addition to the services I mentioned here that we've launched, we've also seen partners such as Cisco and Snowflake launching services available over PrivateLink. Thank you for listening. That's everything I had on the deep dive. And so I'm going to try and answer questions next.